Welcome back to Tracing the Sky. So in the last video, we looked at Aristarchus' first big breakthrough. If you remember, he figured out that the sun, moon, and earth make a right angle triangle when all we can see is a half moon in the sky. When he sees that half moon, he was then able to measure the angle from the moon to the sun, right? The amount of turning between the moon and the sun. And with that angle, he was able to recreate the triangle and measure the ratio of the sides. That tells him how much further away the sun is compared to the moon. And so today we're going to start by revealing what that answer is. Hopefully you had a chance to do it yourself, but I'll reveal to you what the answer is and what the real measurement is and what the real answer is going to be. So let's have a look together. Okay, here we are, and this triangle should look familiar to us, right? This is the triangle that Aristarchus drew when we have a half moon in the sky, right? This is how he imagined the star, the sun, and the moon arranging themselves, or how they had to be arranged in order for us to see that half moon. Now recall that he measures this angle here and that it's close to 87 degrees, right? This angle here is close to 87 degrees. Now in reality, I told you that it's actually a lot closer to 90 degrees, about 89 degrees. So in order for this to be even 87 degrees, it has to be a lot closer to 90 degrees, right? This would be around a 90-degree angle, so just a little bit less. And in order for that to still create a right angle triangle, you would have to move the sun much, much further away, right? These lines are not parallel, so eventually they'll meet. And I suggested that you draw a triangle with the 87-degree angle, figure out where those lines meet, and then measure the sides, and then draw a triangle with an 89-degree angle and see what the difference is. So hopefully you had a chance to do it. If you didn't, pause. I really recommend you go do that and then hop back here and we'll talk about what you would have actually measured if you did that. Okay, well, I hope you had a chance to draw those triangles. Let's start with the one Aristarchus would have drawn, right? Using his measurement of 87 degrees. He would have discovered that the distance from the Earth to the sun compared to the Earth to the moon was 19 times further. The sun is 19 times further away from the Earth than the moon if you use an angle of 87 degrees, right? Set aside whether that's correct or not. That's really far away, much further away at least than the moon, 19 times. That's quite a bit, right? Well, how much of a difference does a 3-degree angle make, right? You might think that's a really small difference, right? Only a few degrees off. Surely the distances aren't that much off. Well, if you drew that second triangle, if you drew a triangle with an 89-degree angle, or an 89.85-degree angle to be exact, you would have found that it makes a big difference. In fact, the sun is actually closer to 400 times further away from the Earth than the moon is. It is way, way, way further away from the Earth than the moon is. Way further than Aristarchus gets. And so even though he's only a few degrees off, that small amount of error actually makes a big difference. Now, I want to remind you, it's still miraculous what Aristarchus is able to do. His reasoning is bang on. He just doesn't have the tools yet to figure out the actual angle. But if he would have been able to calculate the correct relative distance. But regardless of his accuracy, he still has shown us a few really important things. He understands the relationship between their orientation and the moon that we see. He understands what kind of shape that must make. He understands that the sun is much further away from the Earth than the moon. And this is one thing that's really important. He realizes that if he can figure out the distance to the moon, he can then figure out the distance to the sun. So that focuses his attention on the moon. Now, once he figures out the distance to the moon, he's not going to get the right answer, right? If he just multiplies that by 19, we know he's going to be way off. But it does focus his attention in the right place. He's going to focus on the moon because it's a lot closer to Earth. And so he figures, okay, well, let me see if I can figure out the distance to the moon and the size of the moon. And we'll see how he's able to actually do that quite accurately. So let's look at that next step. Okay, so Aristarchus is going to focus on the moon. Now, he wants to see if he can figure out the distance from the Earth to the moon. Okay, distance from the Earth to the moon. That's going to be his primary goal. Can he figure out that distance right there? Now, he's thinking about this, and he knows that the moon goes around the Earth, right? So he can represent that as a circular orbit. So let's do that for him here. So he represents the moon's orbit as a circle with the center being the Earth, right? And what he cares about is the distance from the Earth to the moon. Well, he realizes something when he looks at this. And if you study any geometry in circles, then this red line might represent something familiar to you. This is what we call the radius of the circle, right? In this case, the circle is the orbit of the moon around the Earth, and the radius is the line we draw from the center of that circle out to the moon. Well, this also happens to be the distance from the Earth to the moon, right? So he now knows that the distance from the Earth to the moon is the radius of the moon's orbit. So why is that really important? Well, if you studied some geometry, you might know that there are some really interesting relationships between the radius and the circumference. I'd recommend pausing the video here and checking out the link I've included below. It will go into a deeper dive. It's a short video, but it will give you a nice deep dive into how you can understand the relationship in more detail. I won't cover it in too much detail here, but I definitely recommend watching that video. It's short, like I said, and it'll give you a good understanding of the breakdown and how the Greeks knew about this. Because remember, Aristarchus knows a lot about geometry, as a lot of the Greeks back then, and he understood not just about triangles, but also about circles. So check out that video and then come back once you're ready to learn about that relationship. Okay, so I hope you watched the video. I'll do a brief recap just so we're all on the same page. So we already have talked about the radius, which is the distance from the center to the outer edge of that circle. Well, if you measure across the circle passing through the center, that's what we call the diameter. And it's just twice as long as the radius, right? You think about the diameter as just being drawing two radii in either direction from the center, right? You're going from the center out 2 times the radii. So that's the diameter. This outer perimeter, right, this length around the circle is called the circumference. The circumference is the length of the circle around it, right? So around the circle. Imagine you took a string and you wrapped it all the way around the circle, then you laid the string out flat and you measured the length with the ruler. That would be the circumference. So we've got radius, circumference, and diameter. Okay, well, the Greeks didn't just know a lot about triangles. They actually knew a lot about circles too. And they discovered that there is a relationship between the circumference of the circle and the diameter. Now, this can probably seem a little intuitive, right? If you make this circle larger, you can see that, well, the diameter is going to be larger, right? We've got some extra space here because we made it bigger, and so we need to measure a larger diameter to span the circle. And you can also see that the circumference is larger too, right? It's taking up more space than if it's smaller, right? Just a smaller amount of circle means a smaller distance around it. So there's obviously a relationship. Bigger circle, you get bigger circumference and diameter. But what the Greeks learned was there was an exact relationship. The amount of diameters to circumferences was the same no matter how big or small you drew the circle. So if you measured the circumference, right, you took a string and you wrapped it around the circle and you measured that length, it would always be equivalent to about 3 and a little bit diameters. 3 and a little bit diameters. No matter how big or small the circle, there are about 3 and a little bit diameters to the circumference. Now, what's that little bit? Well, it's a very famous number you've probably heard of. You've probably heard of this number, pi. So there are 3.14 approximately diameters to the circumference. We can write that like this, right? The circumference of a circle is equal to the diameter times pi. There are 3.14, you might know that number, diameters to every circumference. That is hugely significant. No matter how big or small you draw that circle, if you know the diameter, you can multiply it by pi and figure out your circumference. Now, there are 2 radii to every diameter, right? 2 radii to every diameter. So another way to write this formula is that the circumference is equal to 2 radius pi times pi. 2 radius times pi. 2 radius is equal to the diameter. You may have also seen it written like this. Circumference is equal to 2 pi r. Just a rearranged way of saying the same thing. There are 2 times pi times r, doesn't matter what order you put them in, to every circumference. So if you know the radius, you multiply it by 2 and by pi, and you get the circumference. And that relationship matters and is true no matter how big or small you draw the circle. Notice again something remarkable Aristarchus is able to do. He's able to take what he knows about a geometrical shape. Last time it was a triangle, this time it's a circle. And it doesn't matter if he draws that circle in the sand, on the palm of his hand, or imagines that circle to be as large as the orbit of the moon. Really, really big. The principles hold. Now you'll notice something very interesting. What is the radius of this circle, right? The orbit of this circle is equivalent to 2 times pi times this radius, right? Well, this radius is the distance from the Earth to the moon. So another way to say this is the circumference of the moon's orbit is equal to, it's equal to 2 times pi times the distance to the moon. Okay, let me just move that down here so we can see that a little bit better, and I'll just re-emphasize that. The circumference of the moon's orbit, this distance around the Earth, right? This circumference, this orbit, this distance is equal to 2 times pi times the distance to the moon. Okay, this distance here is the radius, so I just swapped out the radius for distance to the moon. That's all that the radius means. If you multiply that by 2 and by pi, you get the circumference of the moon's orbit. This is very significant, but why? Well, let me explain that next. Well, looking at it this way is really important for Aristarchus and what he's going to imagine next. He starts to wonder whether there's a relationship between the diameter of the moon and its orbit, right? Remember, Aristarchus cares about 2 things. He cares about how far away from the Earth the moon is, but also how large the moon is. He wants to find both pieces of information. And so he thinks to himself, what if I take the moon, right? What if I draw little circles representing the moon? And what if I can figure out the diameter, right? Which is just the amount, the distance across the moon. If you were to measure how big the moon is in terms of its diameter, measuring across it, what would that be? And what if I stacked a bunch of moons one after the other? What if I figured out how far across the moon was, and I was able to stack many, many moons across the entire perimeter, right, of this circle, touching each other? How many moons could I fit around here? And if I can figure that out, he thinks, well, I can create a relationship between the size of the moon and the distance to the Earth. And so that's exactly what he does. And in the next video, I'll show you how he's able to figure out the diameter of the moon, or at least a pretty close approximation to it. So join me next time, and we'll continue our journey looking at Aristarchus and his mission to figure out the distance to the sun and the moon and their sizes. I'll see you next time.